Let's jump right into this explainer. Have you ever just looked up on a perfectly clear, sunny day and thought to yourself, why is it exactly that color? We're going to explore the fascinating natural physics hidden right above our heads.
It's a wildly relatable question, right? But the answer is actually deceptively complex. To figure it out, we've got to sift through the actual preserved notebooks of a 19th century British lord. Because, look, while air itself is totally colorless, like a glass of it would just look like a glass of nothing, the secret to why our sky looks like this vast blue ocean, well, it's hidden inside a series of really eclectic, brilliant, and honestly, beautifully chaotic scientific diaries.
Here's our roadmap for today's archival journey. First, we'll head inside the Rayleigh archives. Then, tackle the blue sky mystery. After that, the math of light scattering, followed by sunsets and planetary atmospheres, and we'll wrap up with a legacy of natural physics.
All right, Section 1, Inside the Rayleigh Archives, the MS-63 Collection. So John William Strutt, the third Baron Rayleigh, he wasn't your standard hyper-specialized physicist. No, he was an obsessive documenter of absolutely everything in natural physics. I mean, literally everything. He was this brilliant polymath who would draft what would become Nobel-winning discoveries on the literal backs of scrap paper. His notebooks are just this incredible treasure trove of a mind that basically couldn't stop asking, well, why?
Just take a peek at the contents of Notebooks 5 and 6. This perfectly illustrates a mind constantly racing between wildly different topics to decode the mechanics of nature. In one sitting, he's jotting down notes on the acoustics of organ pipes and the physics of soap bubbles. And then he's comparing direct sunlight with the zenith blue sky, testing human color vision, and then bam, he pivots to the dynamics of steam jets, bird calls, and electricity. He just really wanted to understand the underlying code behind the entire natural world. To give you an idea of his relentless pursuit of precision, it led him to this exact density ratio of oxygen to hydrogen. He figured out it was exactly 15.882 to 1. And noticing tiny anomalies in those gas densities during this exact work, that ultimately led him and his colleague, Sir William Ramsay, to discover the noble gas argon, which actually scored Raleigh a Nobel Prize in 1904. But, that's really just the prelude to our main story.
Section 2, The Blue Sky Mystery, manuscript number 8 from 1871.
Let's trace this timeline because it really builds on centuries of pretty wild guesswork. Back in the 1500s, Leonardo da Vinci poetically guessed it was warm vapors causing the blue. Fast forward to the late 1600s, Isaac Newton thought it was interference colors from thin films. Then in 1859, John Tyndall proved experimentally that suspended particles scatter blue light. But Tyndall thought it was dust and water droplets doing it. It wasn't until 1871 that Rayleigh derived the mathematical law proving that the invisible gas molecules themselves were doing the heavy lifting. And to cap the whole thing off, Albert Einstein definitively proved Rayleigh's molecular formula later in 1911. So the real game changer here is that Rayleigh correctly realized we absolutely do not need dust or haze to make the sky blue. Tyndall thought that totally clean, optically empty air wouldn't scatter light at all. Rayleigh proved him wrong. He showed that nitrogen and oxygen molecules alone are entirely enough. They are literally the atmospheric canvas. Moving on to Section 3, the math of light scattering. The physics of color. Rayleigh defined this phenomenon, which the scientific world now universally calls Rayleigh scattering. Simply put, it's the dispersion of light by particles that are incredibly tiny. We're talking a radius less than about 1/10 the wavelength of the light hitting them. And the golden rule he derived from all this is that scattering intensity is inversely proportional to the fourth power of the wavelength. Okay, I know that sounds a bit heavy, but let's break down what that math actually means for our eyes. When we compare these wavelengths directly, it becomes super clear why the short, tight blue waves crash into molecules and scatter everywhere, while the long red waves just kind of roll right on by. Blue and violet light have very short wavelengths, around 400 to 450 nanometers. Because of Rayleigh's fourth power law, they are incredibly efficient at bouncing off air molecules. Red light, though, it has a much longer wavelength, around 700 nanometers. It's essentially too big to interact much with those tiny air molecules. In fact, if you plug the exact math into his formula, so comparing 700 nanometers to 400 nanometers, violet light actually scatters an incredible 9.4 times more strongly than red light. It's not even close. Even standard blue light scatters about 5.5 times more efficiently than red. This graph beautifully brings that math to life. The dashed line you're seeing is the raw spectrum of sunlight outside the Earth's atmosphere. The dotted line is Rayleigh scattering law in action.
heavily weighted toward the short blue wavelengths on the left side of the chart. And that solid curve at the bottom, that is the resulting product. That's the precise visible scattered light that bathes the Earth. It's literally the mathematical signature of our blue sky.
Now hold on, you might actually be asking yourself this exact question right now. If violet scatters nearly 10 times more efficiently, shouldn't the sky be this vibrant, deep purple? Well, the answer is twofold, and it's super fascinating. First off, the sun emits less violet light to begin with compared to blue. And second, human biology steps in. Our eyes are just way more sensitive to the color blue, so our brain processes that overwhelming wash of scattered light as blue rather than violet.
Section 4. Sunsets and planetary atmospheres. Scattering at scale.
This is where it gets cosmic. The exact same mathematical law that paints an Earth's sunset also defines the atmospheric colors of distant gas giants. Think about a sunset. It's red because the light has to travel through so much more atmosphere to reach your eyes. All the blue is scattered away, leaving only those long, stubborn red wavelengths. It's also why distant mountains look slightly blue, an effect known as aerial perspective. And incredibly, Rayleigh scattering is a huge reason why Uranus and Neptune look the way they do. And it dictates the light behavior in the equatorial regions of Jupiter and Saturn too.
It's such an incredible reminder of why this matters and what you should really take away from this explainer. The tiniest, microscopic interactions, invisible air molecules bouncing light waves, dictate the grandest, most beautiful visual vistas we can possibly observe, not just here on Earth, but all the way out in the cosmos.
Bringing it back down to Earth. Section 5. A legacy of natural physics. A family obsession. Passing the torch, his son, Robert John Strutt, the fourth Baron Rayleigh, took up the mantle, and he was a highly accomplished physicist in his own right. He meticulously logged thousands of his own experiments on gas phenomena and the night sky across 22 original notebooks, and yep, those are also preserved right there in the MS-63 archive collection. Just take a look at this catalog of Robert's notes. Between 1923 and 1935 alone, he was logging observations on the spectrum of the night sky, auroras, the twilight sky, and tracking the nitrogen bands and the very last residues of daylight. This family's shared obsession with unraveling the mysteries of light and atmosphere, it was practically written into their DNA.
So, armed with the secrets of the Rayleigh archives, I really hope you never look at a blank blue sky the exact same way again. Every time you look up, you aren't just staring into some empty void. You're witnessing a mathematical masterpiece. Are you seeing empty air? Or are you seeing a vibrant, vibrating mosaic of scattered light relentlessly crashing into invisible molecules just like Lord Rayleigh calculated over a century ago? Definitely something to think about next time you watch a sunset.